Swayam Prabha. Digital India. Educated India.
Welcome to today's lecture. In the previous classes, we had a brief overview of mineral deposits formed by magmatic and sedimentary processes. Before we move over to the other processes of mineral deposit formation, it would be worthwhile to have a discussion on one of the very fundamental aspects of mineral deposits, which is not only important from fundamental point of view, but also it is important from practical point and utilitarian point or economic point of view as well. So, that is basically the morphology of the ore bodies. Morphology means we mean precisely what is morphology is the way in which an ore body is disposed in 3 dimension in association with crustal rocks in any segment in the earth's crust. And in the course of our discussion on the magmatic deposits, we have had a look on the magmatic deposits like the chromite deposits, nickel sulfide deposits occurring in ultramafic complexes and also with intermediate rock composition, and they occur in a stratiform manner, almost mimicking the sedimentary strata, and we have seen that they are a result of crystallization differentiation of a parent basaltic magma. And such kind of ore bodies generally, if they are not very deformed, they do preserve their pristine characteristics, layered characteristics, as we have seen in case of the Bushveld complex. And the other example that we saw is that of the kimberlite pipes, which occur typically in the carrot shaped form as diatremes and the dikes that are exposed on the earth surface with prominent features. And there it's very characteristic, and also it gives us very fundamental idea about the process in which the body has formed and come into existence. Morphology of the ore body gives very fundamental idea about the process, as we have seen in these 2 examples that we discussed. And then morphology has got a very important role to play in all other deposit types that subsequently we will be discussing some of the important classes as the hydrothermal deposits. So, before we go to look at the process in details, it would be worthwhile to discuss a little bit about the various ways in which such kind of deposits can form in the earth's crust, can be present in the earth's crust. The morphology we study, so the 2 main important aspects. It's very fundamental, is one of the very fundamental attribute, is one of the very fundamental attribute of ore-genetic importance. And number 2 is that the morphology of the ore body needs to be ascertained. It's a must for any mineral deposit which is discovered and is going to be economically worked out. So, this particular deposits, it's very important that its morphology be worked out for economic viewpoint, because essentially the morphology decides the very way, the very method by which the ore deposit will be mined or will be recovered or will be exploited in any particular mineral deposit where this ore body has been discovered. So, the initial stages of the searching for this ore deposit, and after the presence of an ore body is confirmed, which we will be discussing in our later part of this course lecture series when we discuss detailed about the exploration methods. So, once the ore body has been identified or is known to be existing, it is very important to work out the three-dimensional disposition pattern in the crustal rocks. So, that decides, that is a very important aspect which decides the method of mining, the mining method that is to be adopted, because there are certain parameters that comes to consideration is that in order to exploit a particular ore body in any situation existing in the crust, it is very important to estimate that how much of the rock which are not economically important to us, but are occurring as what we call them as overburden. What we call as overburden is any amount of material, either weathered rock mass or any later deposition of sediments or soil or any other unit, any other entity that are associated, which are generally known by the term overburden, has to be removed in order to exploit the ore, the unit mass, any amount of ore from the ore body. So, that ratio, the amount of ore to be, amount of rock or amount of overburden to be removed to get a unit mass of the ore, which is known as the stripping ratio. Is an important economic parameter which comes into existence. So, understanding the morphology of the ore body is of paramount importance in economic geology, in study of the ore deposits, and also the later economic activities. So, as far as the hydrothermal deposits are concerned, the detailed of which we will be seeing in terms of the process in the coming lectures, can be generally be divided or can be classified into into the two types, as cavity filling or as replacements. So, cavity filling, the term is very self-explanatory. So, wherever there is a cavity that is made in the rocks by natural process, so that cavity is basically open for fluid infiltration and fluid circulation. So, wherever there is a fluid that is occupying in an open space, the fluid will deposit its minerals depending on encountering the appropriate physicochemical conditions, and it invariably we have seen that in the crustal rocks, wherever there are fracture spaces, there has been deposition of minerals by that fluid which circulates in the fracture, and this gives a very good idea as to the clear cut symmetry can be very well observed here. We see that from this is the core, or this is the center of the vein that we see here. This is the center of the vein, and the deposition of materials on the either side of the center has taken place very symmetrically. So, we are seeing here that blend standing for zinc blend, there is sphalerite, then barite, fluorite, quartz, then again blend, and again wall. So, likewise we see that there is a symmetry that exists on either side of this centrally placed deposit. So, this generally happens with gradual opening of the fracture and deposition of minerals in this particular sequence. Here it is an example in which same thing which we call them as the comb structure or cockade kind of structure, which mimics that of a comb, which you can be seen very clearly here as this is the fracture space where the crystals are basically deposited on the fracture wall and they project with their projecting faces and very much look like a comb, and these are normally the comb structure. And this is a magnified view of that. We could see that there are many different generations of quartz plus ore mineral, again quartz plus ore mineral, which happens in a typical cavity filling situation. So it's called as cavity filling. It is just because it's filling up the cavity and filling up the cavity by the deposition of the minerals. And these are typical of the situation where we could see that this is a sequence of sedimentary strata and there are faults. So the fluid which have gone into the fault have deposited the ore minerals and have just followed the bedding plane in forming the flat branches of whenever there is an impervious rock. For example, there is a calcareous rock which is served as a rock through which fluid could move, and whereas the shales are more impervious than the limestone, and the deposition of the ore minerals in this form has only happened wherever there it has got the fluid has got a favorable channel way, and although the main channel way has been the fracture for the fault. So this is an example of a fault controlled ore body. This is an example of this is situation similar in a sediment hosted sulfide ore body, which will be studying in some amount of detail in the coming classes. So there we could see that they are very much conformable to the sedimentary strata, which you can see here. So these kind of ore bodies would be simpler to till then they are occurring in undeformed condition or in the crust where have suffered a very little of deformation. So such kind of original pristine characteristics are very much preserved. And this is an example where again a conformable ore body is present along with the sedimentary strata in a sediment hosted massive sulfide deposit. This is the example of a copper mineralization in strata of sandstone. Typically the kind of sandstone hosted copper deposit, stratiform copper is an example from the Zambian copper belt. So these kind of situations here, the kind of mining method that is to be adopted will very much be decided by a proper working out of the geometry of the ore body in the subsurface, the depth dimension, which generally is not easy to be estimated on the surface, but they need a lot of methods to be adopted for ascertaining of their three-dimensional structure, which will be topic of discussion in some of our subsequent lectures. This class of mode of occurrence, which we can state in that way, the different modes of occurrence, is basically is known by a class which are called the fissure vein deposits. So the fissure vein deposits, fissure is any weak plane that is created within the earth's crust because of stress that is applied on the rock because of many different conditions of deformation, or could also be occurring because of solution dissolution of the rock because of fluid. And here there are some diverse situations which are depicted. That in first case it is a chambered type of fissure vein. Fissure is a plane of weakness wherever so they will always have a geometry that the one of the dimensions will have higher than the other two, like is shown here. This is the case where there has been some dilation in the schistose country rocks, and the fluid only could be occupying the zones where there has been dilation. And this is a situation which is depicting several such fissures which are just disposed parallelly, and which you could be called as a sheeted kind of fissures. In this kind of case, it's known as the en echelon kind of pattern, where there are independent lens-wide bodies of fissures which might have opened because of those at the dilational zone, like what we see here. But here they are not connected to each other, and this kind of a pattern is very well known as an en echelon pattern. And this is a situation in which the different from what was shown in this case, as these fissures are interlinked, and all these are marked by these thick lines actually representing the deposition of ore minerals from the fluid on these fissures. Here we are seeing that these fissures could develop either in parallel manner, like the seated ones which we saw. It could be making a radial pattern. It could be occurring as in case of C, this is a radial pattern. In this case, it's kind of a fan. In case of second figure, this kind of a fan. In this case, they are intersecting each other, but they are cognate in the sense that they formed at the same time. This one represents a intersecting system where they are conjugate fractures, means when the stress is applied, the fractures are developing in different geometry abiding by the laws of fracturing. And in this case, it's a again a parallel sheeted kind of fissure system. So all these situations are observed in the brittle deformation zone of the crust, mostly in the hydrothermal deposits. These are interesting situations. So if we have different rock types, sequences of different rock types, and also with depth, when a fissure is developing as a strong fissure and a thick walled fissure over here, and when it transmits, it will always get branched out, and also will be very much dependent on whether it encounters more competent or incompetent rocks. If it encounters more incompetent rock, then the fracture either die out or basically they form a network or branched out, and whenever it comes with a more impervious rock, there the ore is deposited. This is also a situation where there is a shale in which we see that the fracture is thicker, but as and when it enters a more competent rock like a porphyry, it gets almost like form a reticulate kind of pattern. Here it's the case where the fracture gets thinned down when it moves through different rock types. Here it's the case of fracture deflection. Here it's the case of the branching of the fissures when the main fissure from the schistose rocks is entering a more brittle or competent rock here. So these are one of the very important types of morphologies which we get to see in mineralization that occurs in shear zones. So before that, we can just have a very preliminary brief idea about the development of this kind of shear zone. Here, as is shown by the arrow mark here, so there are movement of these blocks in this as given by this arrow, and because of this there are some these are the dotted line actually demarcating the fabric that is developed in the rock, and when the movement occurs in this way, there are some dilational zones which are created within the rock, and they become the locus, they become the loci of deposition of early set of veinlets because of percolation of fluid within this. Because this is a shear zone, there is brittle or ductile shearing of the rock, and there is reduction of volume of the rock, and that allows the crustal fluids to be channelized through this, and they occupy the dilational locales where there are early formed veins. And with progressive shear, these early formed veins, they themselves also get flattened out, and they are also deformed, and if the shearing is progressive or the shearing is again subsequently, there is another generation or another phase of shearing, and with progressive shearing then it also forms such kind of horizontal tension veins, and by the time the shearing has progressed to a very later stages, there we see the early formed quartz veins, they themselves get sheared, and these are very, very common features which we observe in mineralization associated with shear zones. Some of the examples which we will see later on in case of the copper deposits in the Singhbum shear zone, or the gold bearing lode deposits in the Dharwar Craton in India, where there are very much shear control. So shear zones are very important locales, very important elements of study as far as mineralization is concerned, and they do represent a crustal scale deformation. They are sometimes they are very much deeply seated, and they make prominent crustal features such as lineaments which can be observed on the map or from smaller scale synoptic maps. This is an example like this we will be taking up sometime later, but before that, this is a typically deposit, porphyry type copper deposit, and in this kind of a situation we find that the mineralization takes place in a more volume of the granite, and it is associated with lots of dense fracturing because of by a mechanism of hydrofracturing, the pressure that is exerted by the fluid which accumulates and exceeds the yield strength of the rock, and in which case it kind of reticulate kind of fracture pattern which develops, which is generally known by a term called stockworks. Such kind of stockworks are very common in many types of mineral deposits, especially the porphyry type, copper deposits, sometimes in volcanogenic massive sulfide deposits, and also some brittle deformation zone in the crust wherever there has been evidence of fracturing due to fluid or hydrofracturing. We generally see such kind of stockworks generated. This is a picture taken from one sample where the scale could be observed, and what I have drawn here in this sketch representing a stockwork, which is just a dense network of fracture that is generated in a rock because of fluid pressure, and this particular material is an ore in which it has this kind of a stockwork related mineralization of copper, and this copper mineralization has been later been oxidized, giving rise to this kind of this is the pattern that is made or that is formed by the later oxidation product of the copper minerals here, which are malachite, which are the copper carbonate minerals which form because of the oxidation of copper sulfide, primary copper sulfide. It gives a very good idea about what the stockworks are, or what the stockwork mineralization generally looks like. And these are some of the very typical features in deformed terrains. This is this feature which is called the saddle reef, which almost mimics the saddle which is put on the back of the horse, people who ride the horse. So here it's a sketch that how this generally the hinge part of the fold where there is maximum accumulation of the ore here, and such kind of features are observable, and this is a case of a gold deposit in Nova Scotia in Canada, where we could see that this rich these zones where the rich mineralization takes place in most of the areas which are the hinge part of this fold, and many of the layers are co-folded. So this is the feature which is named as the saddle reefs. And there are situations which are also, they look like the fractures which are just like a ladder. I mean, they have been filled up by fluid and there has been mineralization, so they are known as the ladder veins. And these are sometimes there could be features which you could in terms of the morphology, in terms of the mode of occurrence, we could clearly see that the mineralization taken place in the breccia, and such kind of occurrences are observed in many different types of deposits, as you will be seeing them in the subsequent discussions. So these are different types. They could be either a volcanic breccia or a collapsed breccia or a tectonic breccia. Here is an example of a tectonic breccia which is formed within the dolomite, and the mineralization has taken place in this within the spaces created by the breccia, and there becomes a zone which is porous and allows the fluid infiltration and deposition of ore minerals. This is also represents a very interesting situation, which is a brachia pipe type of situation, where this outline indicates that this particular deposit has been worked out by a method of mining, which is basically this from this what is basically shown here. It's a kind of open pit or open cast or you can say surface mining type of method, in which the ore that is occurring within the brachia pipe has been being mined. And from here also we can make some idea as to what we were talking about, the amount of the country rock to be removed to access or to exploit the quantity of the ore which is present here. That gives us a very good idea. So here we could clearly see that the volume of ore which is here, and that needed the material from all these which is shown by the steps, which is the outline of the pit, to be taken out in order to get the ore, and that ore body has been later on been taken out by going underground and adopting to a different type of a mining practice, which is the underground mining. So this clearly demonstrates, clearly justifies to what we initially started the topic as the importance of understanding the morphology or working out the morphology of the ore body, which not only just gives idea about the process by which the ore body is originated, but also important clues and important guidelines by which the exploitation of the ore body could be taken up. And this is a very interesting feature of a brachia pipe, what we see here, and this is almost up to 600, 800 or even 1000 foot, and is deeply seated, and because of some process of brecciation, which could also be because of very explosive fluid activity, which it shows. This tectonic breccia formed by shattering of dolomite, forming what is essentially in the mining geological term is known as ore run. And the deposits, as we first told, that they could be either of the cavity filling type, or the other one is essentially the replacement type, where we could see that this is the main fissure on which the mineralization took place, but the deposition which is formed in the form of has been taken place in terms of the deposition of the minerals on either side of the fracture is not symmetrical, which indicates that there has been some amount of replacement of the country rock through these kind of fissures. This also shows the same situation, and in these cases, wherever it has got a suitable country rock, the deposition of the sulphide minerals has taken place, which is also because of replacement. These are all examples in which the fluid has actually deposited the ore materials or minerals by replacing the country rock selectively by either dissolving the components of the country rock and then depositing the metals in them. And this is a very commonly used term in mining geology literature, which is called the ore shoots. So ore shoots essentially is the enriched part or the rich part of the ore body which is present in an hydrothermal deposit. There are many terms such as pockets, nests, bunches, etc., which are used in the context of this kind of ore shoots. They are exceptionally rich parts, sometimes forming as the bonanza, and which are the zones which are mostly looked for during the mining, and they are generally irregular but more in one dimension. The intersection of the bedding with any fracture where there is a fissure has been created there because of the solution activity, one ore body would be forming, which will be more in one dimension, mostly few tensors. For example, if we have some kind of an intersection type of fissures, then the ore shoots would be forming something like so that will be an example of an intersection ore shoot. They could be either they could be of different types, and they are open space chutes or intersection chute like the one which is shown here, and the previous example were open space chute, well controlled, and there are structurally controlled chutes. Okay, so we come to a close of this discussion on the morphology of the ore bodies, and we saw that it's essentially very important from two aspects, from the origin of the ore body as well as from the economic exploitation of the ore bodies. So, we will continue in the next week. Okay, thank you.